What is this?
You're all good now.
Is it like recording?
It is
Cool.
recording.
Okay, so year 13, everything in circuits we should be able to solve with these two laws, Kirchoff's current law and Kirchoff's voltage law. And so Kirchoff's current law is really, really easy. All it's telling us is that the sum of currents at a node in a circuit is zero. And that comes from like conservation of charge. We can't create charge, we can't destroy charge. So if charge flows into a node, like a junction in a circuit, then the same amount of charge has to flow out. It's kind of like counting cars as they go past an intersection. Like if there's 5 cars go into an intersection, 2 go one way, 3 must go the other way. So it just comes from conservation of charge. It's just telling us that current into a junction must equal the current out of a junction. Kirchoff's voltage law is a little bit more complicated. It tells us that the sum of voltages around any closed loop in a circuit must be zero. That comes from conservation of energy, because voltage is energy per charge. The reason why it's a little bit tricky is that we're going to have some elements in the circuit that add voltage in and others that take voltage out. For instance, when current flows through a resistor, the resistor's dissipating that electrical energy as heat, whereas a power pack adds energy into the circuit. Good. And when we're trying to solve a problem using these rules, it's going to matter whether we're thinking about the circuit travelling the same way as current, or whether we're thinking about the circuit travelling the opposite way to current. If we're travelling the same way as current, we're going to see a resistor dissipating energy, but if we think about travelling the opposite way to current, it's going to appear as though resistors add energy into the circuit. So there's kind of like a little bit of a complexity to how we go about solving circuits there. So we might have a go at the example that we looked at before, see if we can crack it using these rules. Okay, so the first application of Kirchoff's loop law to this problem is looking at the junction, and we can apply the Kirchoff's current law there. We can see we've got 1.2 amps flowing into the junction, 0.8 amps flowing out of the junction. We know that those numbers have to add to 0. We've got 1.2 in, we must have 1.2 out, and so we can see that the current that flows through the loop of the circuit with lamp C must be 0.4 amps. And we kind of know that intuitively that that must be right, but we've formalised it now, conservation of charge. We've got 1.2 coulombs per second going in, if there's 0.8 coulombs per second flowing down, there must be 0.4 flowing across. And finally, we can think about writing down a Kirchoff's loop law for any closed loop in this circuit. And so the way we can do that is, so if we're going to do a voltage loop law, we're going to choose a point to start at, and we're going to choose a direction to go in. And so we might start off down there, and we might progress around the circuit clockwise. And so we know that our loop of voltages is going to add to 0. We know that the first thing we get to is 20 volts, and it's a power pack. And we're going through it in the same way that current would go. We're going through it forwards, and so that's going to add 20 in. So 20. The next thing we get to is a light bulb, but we don't know what the voltage of that is. And so it's going to be minus IR, because we're going through it the same direction it's a resistor, so it's going to dissipate energy. And then we're going to go around the outside. We're going to go around that outside closed loop, the slim shady loop. And so we can see that this resistor here has got 4 volts on it, minus 4. And so what we can see from that is that 0 is 20 minus 4, 16, minus IR. And so we can rearrange that to make it IR is equal to 16. And we know how much that current is. We know that that's 1.2 amps. We know that this voltage must be 16, and we can determine the resistance of that resistor by solving R equals 16 over 1.2, which is some ugly number, isn't it?
13.33. 13.33.
13 1/3 ohms. And so what you'll notice, we chose to do just one closed loop. Interestingly, we could also choose this closed loop here, and we could go around this loop here, and we could say that 0 must equal, we're going through that bulb the opposite way to current, so it's going to be plus IR, and then we're going through this one the same way as current, minus 4. And so we can see in that case that IR is equal to 4. And so the voltage, we've just proven the parallel resistors have the same voltage, right? We've proven that that's 4 volts, and R is equal to 4 over 0.8, 5 ohms. So what we've got is 2 new tools. We've got a current at junctions adds to 0, and a voltages around any closed loop add to 0. We're going to use those tools this year to solve any circuit problem we get.